A very good morning to all present over here. It's our third day. So I again welcome all on the third day of the FDP program entitling the emerging trends in the geotechnical engineering. Hope you have found the session informative over the last 2 days where we have to see the concepts and the challenges which are faced on the field in the area of the deep foundations. And also we have looked upon the emerging areas in the geotechnical engineering with the applications of the nanotechnology and the biogeotechniques in case of the challenging soils. So before starting the today's session, one announcement is there. Due to some unavoidable circumstances, the session 3, which was taken up by the Dr. Jaikumar Shukla, that has been replaced by the Dr. Kalicharan Modak. So our session 3, today's session 3 will be taken up by the Dr. Kalicharan Modak on the key highlights on the National Education Policy 2020. And the session of Vijay Kumar Shukla will be taken up tomorrow in the third slot. So all the details regarding the changes in the sessions will be mailed to you, as well as it will be posted into the our WhatsApp group. So just be updated in that. And as you all are aware that those who have not joined the WhatsApp group, we request that kindly join the WhatsApp group so that all the updates regarding the FDP you can take over in the WhatsApp group. And I request the participants to post their questions in the question and answer box during the sessions, which will be taken up at the end of the session by the expert. So just before the completion of these sessions, we will be floating one Google form for the attendance. So I request all the participants to fill up the attendance form within the half an hour. Because this is as per the ATL policy. So you have to fill up, mark your presence through by filling up this Google form. So I request all the participants to timely present in the sessions and mark your attendance. And so with this, we will be starting our today's session. So for today's session, we are having with the topic of the load and resistance factor design for the geotechnical engineering problems that will be delivered by the Professor K.N. Seth, sir. Professor K.N. Seth is currently professor and head department of civil engineering and dean of faculty of technology at Thamsin Desai University in India. Sir has graduated in civil engineering in 1984 and did his master's in the geotechnical engineering from IIT Bombay in 1987 and master's in the structural engineering from GTIT Nadia in 1994. Sir is having the expertise in both geotechnical and the structural engineering fields. Sir is also having the professional involvement in the subsurface investigations for projects in various governments and non-government organizations like Sada Sarovar Nigam, Narmada Nigam Limited, and Kutch irrigation projects, Yamuna Sabarmati river link projects, and many more. Also, in the computer-aided analysis of the pile or the pile groups which are subjected to the axial and the lateral loads, beam, rough foundations, support on the soil models using the Z soils and the Geo5 for the geotechnical engineering, including the soil structure interaction applications. Addition to that, sir is also having the proficiency in the structure designing, detailing, placing drawings, as well as audit for the RCC buildings, water tank, industrial buildings, and many more, using the software STRAP and STRATPro. Approximately 100 students under the postgraduates have successfully completed their postgraduate dissertations in the geotechnical as well as in the structural engineering under his guidance. Sir has also reviewed books like the Reinforced Concrete Design by Asan Sinha and Pillai and Manan. So with this, we welcome you, sir, and I request you to take over the session.
Thank you, Saraswati, for the kind introduction.
Yes, sir. Screen is visible.
So, First of all, I'm thankful to CSPIT Changa, the Civil Engineering Department, for inviting me to share these views on the LRFD method. Today, I'll be discussing mainly on the load and resistance factor design for geotechnical engineering problem. Now, here my idea is there is a need for rationalization. See, over a period of time, the people have started using the load and resistance factor design, but still there are so many lacunas into the design method. As a result, we have seen that so many times the reinforced earth walls are also collapsed. One of the reason is the limitations of the LRFD method of design. So today we want to see what is basically the LRFD method of design. To start with, what we will do is, first we will understand what all the design methods are about. Okay, what is the basis for the design methods? So out of various design methods, which design method is good, what are the limitations of different design methods, and why there is a need to go for LRFD method of design. LRFD method of design is very well accepted in the structural engineering, but as a part of geotechnical engineering, there are certain problems before we implement the load and resistance factor design for geotechnical engineering problems. So we'll see how it can be rationalized also. So the structural design philosophy, the codes have already progressed from working stress method of design to the limit state method. As you know, RCC design, it has transformed from 1964. It was a working stress method of design, and then in 1978 it has become the limit state method of design. The steel structures, earlier it was the working stress method of design 1984, and then 2010 it has become the LRFD method or limit state design. In working stress method of design, basically any design method, what we want to ascertain is the structure should not fail and it should be service. It should remain in service. So in working stress method of design, what we do is we attain margin of safety with reference to the material strength, dividing it by a factor of safety. So material strength divided by factor of safety is equated to the working load to attain the margin of safety. For RCC design, working stress method was assuming a factor of safety 3 for flexure and factor of safety 4 for compression for concrete, and for reinforcement it was 1.7. For steel structures, working stress method of design is assuming a factor of safety equal to 1.7. So mainly it is because of the loading uncertainty, material uncertainty contribution is very less. So the limit state method of design for RCC structure is implemented in 1978. And this method was adopted using a partial safety factor approach. So in place of having only one factor of safety, that material strength is divided by a factor of safety, two partial safety factors are used. These partial safety factors are for the loads as well as for the materials. As is seen in the table, the partial safety factor for the load is a multiplier. Partial safety factor for load is a multiplier. That means the working loads or the characteristic loads are multiplied by these factors 1.5, 1.5 for dead load imposed load combination. And if the earthquake load combination along with dead and imposed load is there, the partial safety factor is 1.2, 1.2, 1.2. And two different limit states are also defined. One is the limit state of collapse and another is the limit state of serviceability. So these are the partial safety factor for the loads, as well as there are partial safety factor for the materials. So the partial safety factor for the loads are multiplier, whereas the partial safety factor for the materials are strength reduction factor. So for concrete, partial safety factor is 1.5, and for the steel reinforcement, it is 1.15. Here, partial safety factor is considered 1.5, but for the cube strength, a conversion from the cylindrical strength to the cube strength, the factor 1.5 is also used. So it becomes 2.25 for concrete. So here we are using two partial safety factor in our IS 456, whereas for the design of RCC structures, ACI 318, it is using load and resistance factor design. That means there are three partial safety factors. One partial safety factor is for loads, another is for materials, and third partial safety factor is for resistance calculations or preference of the resistance. So let us discuss what are the various requirements for a design. What are the design criteria for designing a safe building, safe structure? Okay. So what are the design criteria? So first criteria is the stability criteria. The structure should remain stable. Okay. So stability is referred with the global supporting system. It should not overturn, it should not slide physically. If suppose there is a simply supported overhanging beam, if load on the overhang is very large, it will be overturned. Okay, so there is a convention, no? So whenever there is a simply supported beam with an overhang, the support portion should be 1.5 times the overhang portion. So to ensure the safety factor of 1.5. So one of the design criteria is stability check. It is irrespective of the material, irrespective of method of design. It has to has a factor of safety minimum 1.55 for overturning and sliding. It is mentioned in the IS 456. The another criteria is safety. So safety is assured with reference to the collapse state. So collapse is occurring due to failure of a material. So when maximum stress in a material is less than the strength of the material, the state of collapse occurs. Now, in a structure, okay, when there are number of members, the collapse state for columns is considered to be deteriorated, whereas collapse of a beam, it can be considered to be a localized at a particular span. It will be localized phenomenon. So that's why when applying SCI method, a resistance factor to the column is considered a larger reduction of the order of 0.75 or 0.8, whereas for the beam, a reduction factor for 0.95 is considered, because when a beam collapses, the effect is a localized, whereas when a column fails, the effect is a global effect. If a single column fails, in most of the cases, the entire structure is supposed to collapse. The third criteria is a serviceability criteria. However, the structure is safe and stable if the deflections are very large or cracking has occurred, if the vibrations are occurring into the structure is rendered unserviceable. So to assess this behavior under the working load, another limit state is defined, and that limit state is a service state. So these are the three main criteria. Another criteria is durability. Durability means the sustainability against the natural forces. So the resistance to the natural forces is normally assured by material specification. That means we have a minimum grade of concrete M20, that minimum cover criteria, and all other criteria. These criteria are taken care for the durability criteria. So if we see the main objective of the design, as a structural engineer, primarily we will take care of the two states. Stability will be taken as an overall care. Okay, so global care is taken. So mainly detailed design will be carried out for the two criteria. One is the criteria is the limit state of collapse, in which we have to attain margin of safety against collapse state. And another criteria is limit state of serviceability, in which we want to assure a functional structure in the service state. Now we will discuss about various design methods in detail. One by one, we'll see what are the design methods, what are the limitations, what are the advantages, and how it works. So basically, if we look at the structural engineering is composed of structural analysis as well as structural design. The types of the problems handled in the structural engineering are the frame structure. Okay, that means linear structures. A frame is composed of beams and columns, composition of the number of beam and columns, and you are designing it for a single in a single plane, or it may be in the three-dimensional frame. But these elements are linear elements. So in frame structure, it will be a two-dimensional, three-dimensional, or one-dimensional structure, but all the elements are linear elements. Whereas another type of the structure part is considered to be the planar structure. In the planar structure, the components are slabs, shear walls, folded plates, cells, where you have to carry out the analysis in 2 dimensions. So here these slabs are considered to be the plate element which are subjected to the transverse load, whereas the shear walls are considered to be plates subjected to the in-plane forces. So then there are folded plates, cells, etc. All these are the planar structure, the structures in the two-dimensional, for which two-dimensional analysis will be required. What we mean by the structural analysis means, right from the BTech first year, we have started doing this structural analysis as a subject of mechanics of structures. In mechanics of structures, what we do is we establish the relationship between the external reactions, internal forces, then internal stresses, then strains and deflections. So first thing is to calculate the external reaction, whether it is a determinate structure or indeterminate structure. First thing is to calculate the external reactions. Then after calculating the external reaction, the structure has become now determinate to find out all the internal forces. So once the internal forces are induced, we want to find out, because of these internal forces, suppose it is in a beam, the internal force primarily induced are the bending moment and shear forces. So if this bending moment and shear forces are induced, what are the strains created? What are the deformations produced? So that's why we are making the relationship of force to stress, stress to strain, and strain to deformation. That theory of bending is one of the relationship which is primarily used for this analysis. M upon I equal to F upon Y equal to E upon R. So that M is the internal force bending moment, internal stress is the F, M upon I, F upon Y, and the deformations are called, calculated based on the 1 upon R, that is curvature. So this is the structural analysis that we are required to carry out for the design. Now for analysis, we are having different methods of analysis. Elastic analysis, where we are considering this structure has to behave within the Hooke's law. Okay. Then plastic analysis means you are analyzing the structure when it is in a mechanism state. A mechanism is formed. The structure is analyzed in the collapsed state. So after forming the number of plastic hinges, we carry out the analysis, and that particular analysis is called plastic analysis. Non-linear elastoplastic analysis. If the structure is behaving in between the two states, it is neither in the elastic state, not in the collapsed state. In that case, we will have to carry out the non-linear elastoplastic analysis. Now, once you have different analysis method, the design methods are, the first and foremost method is the working stress method, as we have said, where you are having a factor of safety for the material strength. The ultimate load method, it induces a load factor which will be multiplied to the characteristic loads. The limit state method, as we use in the RCC design, is 2 partial safety factor method. The limit state method, which is used by the ACI 318 code, is a 3 partial safety factor method, which is also known as LRFT method. So our steel structures, they are using 3 partial safety factors approach. So they are all LRFT method. In the geotechnical engineering, the attempts are also made to implement the LRFT method. Now you see, when we are saying elastic analysis and plastic analysis, whichever method you are using, you have to use accordingly the analysis method. Suppose working stress method you are using, your loads are divided by, your strength is divided by a factor of safety. That means you are in a elastic range. So for working stress method of analysis, working stress method of design, the corresponding analysis method has to be elastic analysis. Now in the ultimate load method of design, what we do is we attain the collapse state. So the ultimate load method is corresponding to the collapse state. So corresponding to the ultimate load method, the method of design has to be plastic analysis. So if you are doing analysis with the elastic method and designing it with the ultimate load method, it doesn't work. Okay, so for ultimate load method, what we have to design is we have to design it with the plastic analysis. And limit state methods, all these both the limit state methods are at the intermediate state. They are neither in the fully plastic state, not in a complete collapse state, because we are already having a partial safety factor for materials. However, we say that the limit state of collapse is with a load factor of 1.5, but it is not the collapse state because there is a partial safety factor already there for material. So it is not a collapse state actually. There is a margin of safety with reference to the collapse state is already there. So for the C and D, The actual method of analysis has to be non-linear method of analysis, which is elastoplastic analysis. And let us see what difference it makes. I'm taking a very simple problem. It is a two-span continuous beam. Okay. So when we are carrying the moment distribution analysis, if we see the bending moment calculation after the moment distribution, support moment at B is equal to minus 144. Span moment for the end span is 115, and span moment for the middle span is 36 kilonewton meters. The problem is very simple and it can be done very easily with the moment distribution. But if I am going to the plastic analysis, what is the requirement for plastic analysis? It has to form one hinge at the midspan of AB and one hinge at the B, support B. So after formation of this two hinge, the bending moment will be same at the midspan as well as at the support. So at the midspan, the bending moment is increased from 115 to 123, and at the support, the moment is reduced from 144 to 123. So if you are doing working stress method of design, elastic analysis values are required. Now in the plastic state of design, here for the end span, bending moment is 123 minus 123. And if you are doing plastic analysis for the second span, the bending moment here is 90. So you can visualize that, see, all of us are using limit state method of design. We are doing the limit state method of design, and the analysis, how we are doing? We are doing the analysis with the elastic method of analysis. So whether you are using any software, ETABS or STAID or anything, it gives you the design in the elastic state only. So for the elastic state, it is a bending moment equal to 36. For plastic state, the bending moment is equal to 90. And for an intermediate state, it can be somewhere in between 36 and 90. So whenever I'm designing for this particular midspan moment, I should provide a capacity more than 36 and less than 90. So there is a variation in the positive bending moment in the midspan due to choice of the analysis method. So when you are doing ultimate load method of design, both these two can be 90-90. Okay, so this part is taken care of by redistribution of the moments in the structures. So my point is, when we are talking about the accuracy in the analysis method and accuracy in the design method, you can see what difference the analysis method it brings from 36 to 90, almost 2.5 times. So before we go into the design methods, we understand the design steps. So for the structural system, we first define the structural system with base fixed or hinge. We select the material, means we select the strength deformation parameter. What is the grade of concrete? What is the Young's modulus? All those parameters are selected. Then we proportion the members. After proportioning the member, we find out the loads. Okay, so all types of dead load, imposed load, and earthquake loads are calculated. After that, the analysis is carried out. For all the members, what we do is we calculate axial force, shear force, bending moment, and torsion. So once the analysis is done, we carry out the design. If it is an RCC member, the beam members are primarily subjected to bending moment. So mu upon BD squared, you have to check for the shear force and provide shear reinforcement. If there is a torsion, you have to consider equivalent bending moment and shear force. If there is a column member, you have to design it for axial load and uniaxial bending or biaxial bending as applicable. So once you have done the analysis, you do the design. If the members may not satisfy, in that case, you have to do the iteration. So after iteration, you complete the design and you have to carry out the design detailing process. This is the design process, design steps which are involved in this design of a structure. So now I'll try to explain what different methods of design are. I'm taking a very simple problem. The sitting of the students, it is done on the benches. Okay. So this is a bench on which the students are expected to sit. This is a four-seater. This is a four-seater bench where width of the bench is equal to 50 centimeter. Okay. And these benches are normally produced by, are manufactured using wood. So I'm taking the stress level as stress of the wood 150 kg per centimeter square. Okay, this is an illustrative problem to convey the concept of design. So we are having 4 persons, each of 75 kilograms, sitting onto the bench. So approximately, if I consider the total weight, it becomes 300 kilograms. Now, this 300 kilogram, instead of considering it as a point load, I am idealizing it as a UDL. Okay, so total 300 kg load. If it is idealized as a UDL, it becomes 150 kg per meter. And then the bending moment that is induced, it is equal to WL squared by 8. So 150 into 2 squared by 8, the bending moment induced is 75 kg meter, and maximum shear force is at the support 150 kg meter, 150 kg. So I am trying to design for bending moment. So in the method of analysis, you know that bending moment is equal to theory of bending. It gives you MR equal to F upon Y into I upon F upon Y, okay, into I upon R. So F maximum will be at Y maximum. So what it gives is moment of resistance is equal to sigma Y into Z. So maximum bending moment, if I equate to the moment of resistance of the section, then sigma Y into Z, it gives the value of the modulus of section equal to 50 centimeter cube. Okay. So if I consider design these benches at the limit state only, at the maximum value of the yield point, so that means BD squared by 6 is equal to 50. Z is nothing but BD squared by 6, modulus of section. Most of you will be able to recall. So BD squared by 6 is equal to 50. B is equal to 50 centimeter. The numbers are made very simple. So B is equal to 50 centimeters. So 50 will go. It is D squared will be equal to 6. So D is the thickness of the material, 2.45. What it means is, if I provide a thickness equal to 2.45 and I make all the 4 persons sitting into this at that particular thickness, if the thickness is 2.45, it will collapse. It will be yielding. Why? Because I have just provided the thickness which is just sufficient to carry the load. Slightly more load than the 75. Okay, if it becomes 70 instead of 75, it is slightly more. This is going to fail. Okay, so the section is going to rupture because of this. Modulus is not adequate. So here the critical thickness that is obtained is 2.45. Now we want to make sure that our benches should not fail. Okay, so let us see what to do. So what are the uncertainties involved into this problem? In this problem, what are the uncertainties involved? See, one of the uncertainties involved is in the loading. Okay, right now I have neglected the self weight of the material, but there will be a self weight of the material also. This weight of the students, it can be 75 kilograms. It can be less also. It can be more also. There can be students of 100 kilograms also. Okay, there can be people 80 kilograms, 85 kilograms. So there will be a variable involved in the loading. So what is the variation? All the variation in the dead load, it can be 10 to 20% variation. Here dead load is self weight. Okay, so suppose I have manufactured for 50 centimeter, the benches are manufactured with 52 centimeter. I have given the order for 4 centimeter thickness. They might have prepared it with the 4.2 centimeter thickness. So what is the variation? Variation is there in the dead load. Variation is there in the imposed load. So imposed load variation is 10 to 20%. The variation in the live load is 50 to 60%. So what are the uncertainty that will lead to failure? That can lead to failure. So one of the responsible thing is loadings. The second part is material. Okay. So here I am using wood. I am assuming that the strength of the wood is 150 kg per centimeter square. However, it is produced in the industry. It cannot be 150 kg per centimeter square. There will be some statistical variation. Even for the steel, you see that the variation can be of the order of, we are allowing a variation of 15%. So here there is a variation in the strength of the material itself. So wood being a natural material, instead of 150, it can be less also, it can be more also. So one of the variable is material strength. Second variable is material geometry. Say for example, I have given that my design thickness is 2.45 or my design thickness is 4 centimeter. The material that is received, that is used, it may not be exactly 4 centimeter thickness. There will be certain tolerance I have to allow. Okay. So if the section is instead of 4 centimeter, it might be slightly lesser. Okay. The column section we are putting 300 by 300. It may not be exactly 300. There is a tolerance allowed. It may be 290 millimeter by 290 millimeter. Okay. So there is a reduction in the geometry, is gap in the geometry. So marginal reduction in the geometry should also be allowed. So here the material variable is uncertainties due to the strength and uncertainty due to the geometry. Uncertainty due to the strength is the dominant part. Due to the geometry is less variable. And the third part is resistance calculation. See how I am calculating the resistance. MR is equal to sigma y into SAT. Now whatever are the limitations of the bending theory, the same limitations will be applicable for the resistance calculation. So we know that the theory of pair bending is used. So if the material is homogeneous, isotropic, if it is natural wood, it might not be same isotropic and homogeneous. Okay, so whatever are the limitations of the theory. Another limitation of the theory is it is for a small deflection. If the deflections are going to be larger, then there is a deficiency into the calculation. We are using a linearly elastic model. Okay, so if we are using a linearly elastic model, then the material of the wood might not be behaving linearly elastic. See, concrete, we know that concrete is considered to be having a modulus of elasticity ES is equal to 5000 root FCK. But we have seen that the diagram of the concrete is a parabola. Up to a strain level of 0.002, the diagram is not a linear diagram, it is a parabolic diagram. So there is a uncertainty involved into the three parameters. One of the parameter is loading, another parameter is material strength, and third parameter is the method of calculating the resistance. So what is required is what we need is we want to take care for these three uncertainties. One of the uncertainty is loading. So what we have to do, we need margin of safety with reference to the three parameters. Margin of safety with reference to three parameters. One parameter is loading. So we have to keep a margin of safety with reference to the overload. That means if the person's weight is not 75 kilogram, it may be 90 kilogram, it may be 100 kilogram. So I have to make a provision that all the people, all the four persons that will be sitting, it can be something high. So how much, that has to be decided. That is what we call method of design. So margin of safety for the overload. Similarly, what we have to keep is we have to keep a margin of safety for the under strength. That means the material that is used, it might be having some small margin. If we are preparing 1000 batch for the classrooms, if you are having 1000 benches for the classrooms, out of the 1000, in 5 benches, it may be a lesser strength. Okay, in 5 benches, there may be some lesser strength, then that will definitely collapse. So ratio is only 5 out of 1000, but that definitely fails. So we don't want to take any risk. Okay, so how much margin we want to keep it for the under strength, that we will have to decide. Another margin of safety we require for the simplified analysis method. Okay, so that means if our analysis method is simplified, our the relationship is simplified, in that case we have to give some margin for the simplification in the method of analysis. In the resistance calculation, another margin is also provided, that is called preferential failure. as I give the example that in ACI code, they provide a resistance factor equal to 0.95 for the beams, and resistance factor for the column may be 0.75 to 0.8. The reduced value for the column is the failure of column is less preferred because a single column fails. Okay, so if a column fails and a beam fails, the consequences are not identical. For column failure, there is a global failure. For a beam failure, there will be a local failure. So what is normally done is this can be taken care of. So this particular part, selective failure, it cannot be taken care of by margin of safety in loading. It cannot be taken care of by margin of safety in material. You have to have a margin of safety for resistance. So for column resistance, you can reduce that resistance value to 0.75 to 0.8. And you can keep the value very close to 1 for beam failure. So these are the three margin of safety required. And that's why there are different design methods. If the margin of safety is taken care of with reference to the load only, in which all the three factors are accounted, then it becomes the ultimate load method. If margin of safety is taken care of by material strength, with reference to material strength, we call it a factor of safety, and we call that method as a working stress method. Okay, so all the three methods margins are taken care of, then it is a factor of safety but working stress method. So ultimate load method is the margin of safety with reference to loading only. Working stress method is margin of safety with reference to material only. If we say limit state method, for RCC design, we are having two margin of safety, one with reference to the load, another is with reference to the material. So it is a two partial safety factor limit state design. And the third method of next method of design is, here we have a three partial safety factor, one for the loads, one for the material, and one for the resistance calculation. Then it becomes a limit state method with the three partial safety factors. Limit state method with three partial safety factors. And that we called LRFD method. So that means we are able to understand that we have to take care for the three partial safety factor into the LRFD method, and we have to work out the values. So uncertainties are involved in all the problems of design, whether it is a geotechnical problem or structural problem. What we want to do is we want to assure safety. Okay, and whatever uncertainties are involved, we want to take care for all the uncertainties. Now, how to take care for the uncertainties? Mathematically, that is accounted in the reliability theory. Okay, so this reliability theory, it takes care for the uncertainty to a quantitative, with a quantitative approach. That means there are different reliability levels: reliability level 1, reliability level 2, and reliability level 3. The level 3 is best to define the level of safety. That means whatever may be the number of uncertainties involved, you account for all the uncertainties, you give the data for all the uncertainties. There are Monte Carlo methods and other methods which will calculate what is the probability of failure. The reliability level 3 will give you what is the probability of failure acceptable to you. Based on that, you will have to select the design parameters. So probability of failure which is acceptable is 10 raised to minus 6 or 10 raised to minus 7. So probability of failure 10 raised to minus 6 means one chance of failure in 1 million cases. 10 raised to minus means one chance of failure in 10 million. So this is the exact method of assuring the safety. Okay. But mathematically, if we want to go to the level 3, what we should have is, we should be in a position to have a great quantitative details in loading variations, material variation, okay, then resistance calculations, what are the methods used. So in all the three cases, we should have the number of data, large data available. Suppose we want to take care for the loading, okay. So what is the probability that weight of the person will be exceeding 75 kilograms? Okay, so you should have 1 million data. You should have data of 1 million person. Then only you can find out what is the probability of exceeding these loads. Okay, similarly, what is the probability of reducing the thickness? we should have the data of material. Okay, so that means based on the either the tolerance allowed in the code or the data available, you can work upon the reliability method level 3. So that means it requires large data available. And see, before you build anything, you don't have the data. Suppose you want to find out what is the probability of failure of a dam, then how can you find out the probability of failure of a dam? Because you don't have so many dams available. So many similar dams are available with various different factors. So in civil engineering, basically, what we do is we first develop the structures. Okay, all the structures and whatever is there, it is evolved by experience and expertise of the engineers. Okay, so first the things are evolved and implemented. Say T-Wiley, Freshnet, they have implemented pre-stressed concrete. Okay, based on their experience, they have put it into the practice. And after the practice of after construction of so many bridges, Leonard and Freshnet, all those people have developed various codes, helped in developing different codes. So first thing is to develop the technology based on the expertise and experience of the engineers and based on their sixth sense. Okay, so these are all empirical methods which will be initially available, and then you will get a final mathematical form after so many years. Okay, still we know in the geotechnical engineering, when we are finding out phi value for cohesionless soil. Okay, what is the method of finding out phi value angle of internal friction for the cohesionless soil is? We say direct shear test, triaxial test, unconfined test. Okay, but when you don't have a undisturbed sample, okay, cohesionless soil means you cannot get undisturbed sample from the field. So how to get the value of phi? So we don't have any method of finding out value of phi for a soil in which undisturbed samples are not obtained. So the value of phi is still we are using Terzaghis guideline that you carry out a n value test, SPT test. And from the SPT test, we get the value of phi. From the value of phi, we apply all the reliability method, all other methods, and we say that this is the best method of design. But what is the inaccuracy in the input itself? The input itself is empirical. Input itself is highly empirical. There is a great variation and great uncertainty involved into the input. So that means in civil engineering, complying everything with the mathematics, it's not possible. Okay, so whatever is evolved, whatever is getting developed, what we do is once the things are developed to a certain extent, we give that a mathematical form. Say for example, finite element method, it was evolved for the structural engineering. Okay, for development of the plane, it was evolved. It was evolved for the development of delta plane. And it was evolved based on the matrix analysis of the structures. It was primarily based on the stiffness method. Okay. Now, once the finite element method is completely developed for the structural engineering, then the people have thought of that this is nothing but mathematics. It is the method of variation. So the variational calculations, variational formulation has been evolved for finite element method. And now the finite element method is used for all the branches. It is used for heat transfer problem. It is used for the seepage problem. It is used for the conductance. It is used for the electronic circuit design. Everywhere that finite element method is used. So first finite element method was developed by the intuition for the structural engineering for stiffness calculations. So later on the mathematical tools are developed. So same is applicable to the LRFD method. We say that LRFD method, we should have level 3, but not possible. Okay, so we'll have to satisfy ourselves with certain less than that. Now see the design methods. So we have seen that there are 3 uncertainties. One uncertainty is with reference to the loading, with reference to the material, and with reference to the resistance calculation. So to cater this need, earliest method of design was working stress method. And what we do is we apply a working stress method means factor of safety. And this factor of safety is generally used for the general purpose is 3. For concrete, wood, which are all this material, the factor of safety used is 3. For steel, the factor of safety used is 1.7. So in our this problem where I'm having the maximum bending moment of 75 kg, I was considering this stress level to be 150 kg per centimeter squared. So what I should do now is, now I should apply a factor of safety to this 150. So if I provide 2.45 centimeter thickness of this section, then with this load, it cannot handle any uncertainties. Anything slightly more than 75 kg per centimeter, 75 kg, or the material having slightly weaker than this 150 kg per centimeter squared, it will fail. So to allow for the uncertainties, I am putting a margin of safety with reference to the material strength. Material strength is 150. So instead of 150, what should I do is I should allow for a factor of safety 3. So now I will not consider the stress level is equal to 150 into this equation. Z is equal to 75 into 100 by 150. But what I should do is I should put a margin of safety 3 here. So I'm putting a margin of safety 3. That means my sigma allowable will be used instead of using sigma yield point. So yield point is 150. Factor of safety is 3. So allowable is 50. So my Z required is 150 centimeters cubed. And BD squared upon 6 is equal to 150. Therefore, my D is equal to 4.24 centimeters squared. 4.24 centimeter thickness. So that means by working stress method of design, I provide the thickness of the wood in the benches to be equal to 4.24, say 4.2, 4.3 something, or you say instead of 4.24, you may go for 4.5 centimeter. Okay. So approximately 1.75 inches thickness, 1.75 inches thickness is provided for the benches, and it will be safe. Now it will resist all the, it will be able to tackle all the uncertainties in the loading, uncertainty of material, uncertainty of the strength calculation. So this is working stress method. Ultimate load method. In ultimate load method, what we do is, right now I'm having the weight of the person is 75 kg. What is normally done is, I increase the weight of the person by some factor. Okay, whatever loads are there, I'm not decreasing the stress level. I am increasing the load level. So all the loads are increased by 1.7 times. Okay, so that means approximately 120 kg. If all the people are 120 kg, that will be the collapse state. So 120 kg people will not be possible. So that 120 kg, it has to take care for the material, it has to take care for the loading, and it has to take care for the approximation in the resistance calculation. So next method of design, this was factor of safety method. Now this is a load factor method of design. So what is done? The loads are increased by a factor. So that load factor is 1.7 to 2. So if this is a wood, we are increasing the load factor equal to 2. So mu is equal to, instead of 75, it becomes 150. So Z becomes 150 into 100, mu upon sigma y. So that becomes 100 centimeter cube. So our thickness is how much? D is equal to 3.46 centimeter. So if we are doing it by the ultimate load method, I am getting a thickness equal to 3.5 centimeter. Working load, it was 4.24 centimeter. Here I am having a concept in my mind that when the load becomes 2 times, that means when the weight of the person is 150 kilogram, per person 150 kilogram. So that means I have an idea what can be the overload it can take, what can be the overload it can take. So now the safety margin is known to me in terms of extra loading. So if we now compare these two methods, here margin of safety with reference to the material only. In the ultimate load method, it is with reference to the loads only. Here, when you are using working stress method, there are loads with different uncertainties. I say no, dead load uncertainties are very less. What is the variation in the cross section of the beam, cross section of the benches? Hardly some small variation can be there, 5-10% variation. And variation in the live load is more. So I should not keep the same margin of safety for dead load and same margin for live load. But because there is only one factor of safety, we are having same margin for dead load and live load both. So in ultimate load method, you are having same margin of different load factor. So for dead load, you can have a load factor 1.3. And for an imposed load or live load, you can have a larger factor of safety because this is more uncertain. In working stress method, we have margin of safety with reference to the material strength, and it is not cognizable. That means when it is overloaded, you will not be knowing that how much overload it can sustain. Whereas in the case of ultimate load method, it gives us a physical sense. You said that if you are having a load factor of 1.5, that means at least up to 1.5 part, it is going to sustain the load. So when it becomes 1.1, 1.2, 1.3, we are assured that however it is overloaded, it will not collapse. Another important point in both the design methods is, as I said, in working stress method, we are having a factor of safety against the maximum stress value. So when your maximum stress value is divided by 3, at which level we remain? We remain in a very lower stress value. And lower stress value means it is almost a linear part. It is almost a linear part. So in the analysis, we can neglect the non-linearity. So all the non-linearity we can neglect in the analysis as well as in the design strength calculations. In the ultimate load method, at which state we are designing? Ultimate load method means you are increasing the load to collapse state. So what is the design state? The state of design for the ultimate load method is the peak value. And for that value, you have to take into account the non-linear behavior and the method of analysis. That elastic analysis will not work here. You have to go for a plastic analysis. Okay. So for a non-linear method, for ultimate load method, we have to go for a plastic analysis. So this is what I said. Design stress level is much lower than the collapse state. Non-linearity is ignored. Here, non-linearity is to be taken into account. Non-linearity comes, complex calculation becomes very much complex. Here, when we are doing working stress method, our analysis method and the design method both are linear. Whereas in ultimate load method, when we are doing, normally the analysis is carried out by linear elastic method and design is taken as a collapse state as a non-linear. So there is an anomaly into the ultimate load method. In the working stress method, the design is completely done at the service state because it is factor of safety 3 to the maximum strength value. So it is serviceability criteria is also verified. Here it is at the collapse state. So when if you are doing the ultimate load method of design, what you have to do is we'll have to design it for the limit state of serviceability. I mean the service state also. So collapse state it is designed, but check for the serviceability, we have to make it. So now to overcome the limitation of both these methods, limit state method is evolved. So limit state method is evolved to take care for the margin of safety for materials and loads together. Okay, so working stress only margin of safety for materials, ultimate load method is margin of safety for loads, working stress method is at the service state only, and limit state method is for the collapse state only. So instead of having these multiple partial safety factors are recommended to be used. So the limit state means it will be considered to be designed for 2 states. One is the limit state of collapse and another is the limit state of serviceability. So limit state of collapse means you are having a overloading factor to be multiplied and assuming that the structure will reach the collapse state. So that is a non-linear behavior to be accounted for the limit state of collapse. For the limit state of serviceability, we will have to take care for the linear behavior only. So we have to take care for margin of safety with reference to two things. One margin of safety with reference to the understrength and one margin of safety with reference to the overload. And this has to be taken care in the ultimate limit state method. Okay. So this is the ultimate limit state. And access for to assess the deflection and cracking, what we will call it is SLS, that is serviceability limit state. So ultimate limit state and serviceability limit states are the two limit states that will be verified for the limit state method design. And right now we are going into much details about the limit state of collapse. Because serviceability limit state, the problems are much simple. You are remaining within the elastic range. So the complexity is highly reduced. So in structural engineering, the probability of failure, if we want to see that 1 in 1 million or 1 in 10 million, the probability is assured like this. We plot a variation frequency curve for the loads and we plot a frequency curve for the resistance. So what is the common area? What is the common area between the two? This hatched area is indicating that failure will occur. Okay. So if Q is overlapping with the R, if both these are separated, then there is no collapse. Okay. But to attain that particular strength, to attain that particular level, you have to spend a load. So we have to arrive at a state of compromise. How much should be this hatch region we should allow? How much hatch region should be allowed? So this hatch region, the calculation of this hatch region, it is known as a probability of failure. Okay, out of all this resistance calculation, how much should be allowed within the hatch region? So that is what the reliability method is. In the reliability 2 level, the equation that is formulated is a reliability index. Okay. So remember that mathematics is evolved only after evolving the design methods. Okay. So if you are having certain number of data, based on data, you can have a back calculation for the reliability, and then you can say that my reliability index is this much. So here a curve for natural logarithm of R upon Q is plotted versus frequency. Natural logarithm of R upon Q is plotted with the frequency. A beta factor is calculated. Here, this VR is VR and VQ. Okay, coefficient of variation with reference to the sigma R is the standard deviation. Okay, so the standard deviation upon mean value of the resistance, standard deviation for the load and mean value of the loads. So Rm is the mean resistance, Qm is the mean loading. So this is how the beta factor is evolved. So this is required for those who are finding out how much should be the value of partial safety factors. Okay, so level 3 reliability, level 2 reliability is to be studied by whom? It is not to be studied by the engineer who is implementing LRFD. It has to be studied by the engineers who are developing LRFD. So there are people in the Purdue University, you will find Salgado. There are a number of people which are involved in the development of EC7, Eurocode 7. They are all involved primarily in the reliability methods. So those who are involved in the LRFD development, they have to go into the details of reliability. And we being the user, we will have to use those factors which are provided for the design. Here the basic concept is how those factors are evolved. It can be seen here. That is with the level 2 reliability. And it is seen that even it will be highly complex to go for the level 2 reliability, even for structures. Okay. So the calculation for structures is also very complicated to get the partial safety factor with the reliability theory. So you see that if the beta factor, which is calculated, the probability of failure. So if it is calculated, so 1 in 1 million and 1 in 10 million. What is the beta value? Beta value probability of failure comes to 5%. Okay, so Just, just 1 minute, I have to spare myself. And just okay. So that was a phone call from my sir. Okay. So to assure a reliability of 1 in 1 million or 1 in 10 million, I have to assure a probability of failure 5%. So in the limit state method, we are using a reliability method with the 5% probability. Okay. So those who remember the limit state method, what is the definition of characteristic load is there is having a 5% probability of being exceeded in the life cycle. Okay. So it is very difficult to assess. So whatever is told to us, we will accept. Okay. So when I say characteristic live load is 3 kilonewton per meter squared, which is given in the IS 875. Okay. So IS 875 part 2, if the live load is given for the residential building is 2 kilonewton per meter squared, that live load, it will be treated as a characteristic load, and we assume that it is having a probability of being exceeded 5%. See, even before the limit state method was there, that same live load was used for working stress method. Okay, and that was 2 kilonewton per meter squared. And still after implementation of this, they have accepted that there is a probability of 5% probability for being exceeded in the life cycle. Similarly, for characteristic strength, see, for load, it is a qualitative assessment. You cannot have the variation of load being assessed so many times. It is different at all different places. Now, another parameter is strength. So what is the partial safety factor should be considered? What is the criteria for partial safety factor for the strength? Suppose I am having concrete strength, I say M20. What is the meaning of M20? That 20 Newton per millimeter strength is available, and there is a possibility of having 5% result less than those values. So if I want to find out the what is the characteristic strength, then there is a statistical value given that you test minimum 32 cubes. If you test 32 cubes, and out of that, whatever is the strength attained by more than 95% of the cubes, that cube strength will be considered to be the characteristic strength. So this is the probabilistic approach. Instead of having the reliability approach, the limit state method of design has to satisfy with the probabilistic approach. So what is this probabilistic approach? That whatever loads are there, there is a 5% probability of being exceeded. Similarly, for compressive strength, we have to satisfy that the strength of the material should be, it can be reduced less than the characteristic value for 5% of the results. Okay, so 5% of the results might be having a value less than the characteristic strength, less than the values, okay, prescribed values. So the point is 5% probability. So initially by level 3 and level 2, that for corresponding to 10 raised to 1 in million, 1 million or 1 in 10 million, what is the probability of failure? 5%. So that is derived, and after that 5% is considered as the basic. So now we see our limit state method of design. It is highly simplified now. What you have to do is you have to apply two partial safety factor. Okay. So with characteristic strength definition of the characteristic strength is taken as 5% value. Probability of failure as 5%. Okay. So with 5% probability of failure, the partial safety factor for the loads are designed as dead load, imposed load 1.5, Then dead load, imposed load, and wind load 1.2, 1.2, dead load and wind load 1.5, 1.5 for the ultimate limit state. Okay. So partial safety factor for the loads, gamma, it will be again a multiplier. Okay. Now this partial safety factor for the load, we have discussed earlier that in the working stress method, both the loads are considered at par, dead load and imposed load. However, our IS code is also considering dead load is having a same variation 1.5, imposed load is also having the same variation, same uncertainty level 1.5. See, same partial safety factor for both the loads means we are accepting that uncertainty level of both the type of loading is identical. Level of uncertainty in both the loading is identical. Then only we will put same identical values of the partial safety factor. If we see other codes for dead load, they will put 1.3, and for imposed load, they will put 1.7. Okay. So basically, we have to come at a logical value. So here it is a higher side, 1.5, 1.5. The reason for 1.5, 1.5 is our IS 456 old code. It was derived from the British codes, and the British code has taken up the value of 1.5. I think that is the reason they have adopted also the same guidelines. Similar guidelines are adopted. Similarly, for material strength, they are saying that partial safety factor of 1.5 for concrete is used, and partial safety factor for 1.15 is used for the reinforcing steel. Basically, our partial safety factor is not 1.5 for. Basically, the partial safety factor is 1.5 on the cylindrical strength is used in the other codes. And in our code, we are using cube strength as the criteria for the concrete strength. So basically, what is the partial safety factor? It is not 1.5. Basically, it is 2.25. Our code says that the strength available in the structure is not FCK, it is FCK by 1.5. So why that strength is reduced? Because other codes are following cylindrical strength and our code is following cube strength. So our criteria for testing and everything is laid by cube strength, because from years together it was based on the cube strength. So we carry out the cube strength, and our code is also formulated based to facilitate the existing way of working. So basically, we should say that our partial safety factor for material of concrete, with reference to the cube strength, if we say it is 2.25. So now nominal resistance is proportional to the strength. Okay, now resistance, if you see mu upon BD squared equation, that is directly proportional to the FCK and Fy. So whatever is the resistance calculated, if it is divided by the partial safety factor of material, it has to be equated to loading characteristic load multiplied by partial safety factor for the load. Okay, so our equality is, what we have to equate is resistance upon material partial safety factor equal to loading multiplied by overloading factor of partial safety factor, gamma F. So nominal resistance upon the character strength is equal to gamma M into gamma F. So this is approximately equal to, this is what was resistance in the working stress method. This is what was loading in the working stress method. So resistance upon loading is equal to factor of safety. So gamma M into gamma F, it gives an idea about the factor of safety. So if we consider a crude comparison, because here the partial safety factor will be different for different material, different loading. Okay. But if we consider partial factor of safety for concrete, how much it is? Nominal resistance upon design service lead, Rn upon QCH equal to gamma M into gamma F. Gamma M is equal to what? 2.25 for material with reference to the cube strength. Because I want to compare it with the old working load method, which was in the IS 456 1964. So what was there in the IS 456 1964 was concrete was having a factor of safety 3 for flexion and factor of safety 4 for compression. So with limit state method, how much factor of safety we are arriving at? 2.25 into 1.5. For dead load and imposed load, it is 1.5 gamma F. This is a partial safety factor for the loads. So 2.25 into 1.5 gives you a value of 3.375. That means for working stress method flexure, it was 3. Now we are getting 3.375. Okay, so still your margin of safety is intact. For dead load, live load, and imposed load combination, what we were doing in the working stress method is we were increasing the stresses by 33%. Okay, so by increasing the 33% stress level, we were having a factor of safety equal to 2.56. And if we consider the crude comparison of this limit state method, how much factor of safety it comes. So for partial safety factor for the load is 1.2. Okay, and material is 2.25. So when dead load, live load, and imposed load combination is there, dead load, imposed load, and wind load combination is there, partial safety factor is 1.2, it gives 2.7. So however we are going with the limit state method of design, our basic intuition about the margin of safety with reference to the factor of safety, it is still intact. It is not hampered. This is true for the steel also. So for steel, the partial safety, the working stress method factor of safety was 1.7. So if we consider the equivalent working factor of safety for this limit state method, then what is the factor of safety that is obtained is for the yield governed criteria 1.65, and for the ultimate load governed criteria, ultimate stress governing criteria, you have 1.88. So this is approximately, that means our perception of the working stress method is also satisfied. Our perception with the ultimate load method is also satisfied. Even if we are going ahead with the limit state method, we are taking advantage of the limit state method. Our margin of safeties are intact. Only thing is we are taking advantage of the non-linear range of the stress strain curve of the concrete. Okay, when we are going to the limit state method of design, what is the advantage we are having? The additional advantage is by going up to the 1.5 partial safety factor of 1.5 for the load, we are going to a non-linearity of the stress strain curve. With the non-linearity of the stress strain curve, we are getting higher concrete strength, and with the higher concrete strength, you get the higher value of resistance. Now, ACI 318 format is a 3 partial safety factor format. So there is a partial safety factor for the loads, partial safety factor for the materials, and partial safety factor for the strength. As I said, for the strength, there is it takes care for the 2 criteria. One is the resistance calculation simplicity, simplification of the resistance calculation. And second is preferential failure. So flexural failure is preferred, and it is having a partial safety factor 0.9 for resistance, and axial compression, it is having a small partial safety factor 0.7. So for column, they are using additional margin of safety 0.7. So this much time it took me to explain the basis of the design, because without that we cannot understand what is to be done in geotechnical engineering. What are the problems? Now the problems in the structural engineering are not much as compared to the geotechnical engineering. Even then you have to simplify, you have to come to the level 1 reliability. The structural engineering is not doing the reliability method level 3 or level 2. It has to satisfy with reliability level 1. So now whatever partial safety factor we have for the structures, we want to find out similar partial safety factor and which load combination should be used. Okay, which should be the combination of partial safety factors to be used in different cases. So that is what we want to see, and this we will see in light of the Eurocode 7 mainly. Because IRC is not yet implemented. IRC 78 we have started, but is not implemented. So IS 64053 is used for the way we had IS 456 1964 for RCC design in working stress method. still we have prevailing IS 6403 for bearing capacity calculation. It gives us the bearing capacity factors. Okay. And for getting a allowable bearing pressure, a factor of safety 2.5 is recommended. If somebody asks you that from where to get the factor of safety 2.5, in which book it is, in which code it is written, you will have a great exercise to find out which code gives you a factor of safety equal to 2.5. That is the tragedy of IS codes. IS code doesn't provide you guideline in one set. Okay, IS 6403 is for bearing capacity calculation, but it doesn't mention how much factor of safety should be used for how much factor of safety we have to use for bearing capacity calculations, for ultimate bearing capacity. So you have to search it to the other codes. There are so many limitations of IS 6403 also. So that, but one thing is sure that IS 6403 has been in use from so many years, and whatever performance of the structures till now, whatever performance of cell foundation is there till date, the most of the cases the performance remains satisfactory. So whatever development we take now in RCC, we have compared that what is the margin of safety with limit state method and what is the margin of safety with reference to the working stress method. It was comparable. So similarly, we will also have a comparison of the codes which are based on LRFD method. We will have only the benchmark available is 6403. Apart from all the limitations of 6403, we have the IS 6403 is the benchmark. So now from 1978 onwards, all RCC structures are transformed to the limit state method of design. 2010 in India also, all steel structures are transformed to limit state method of design, but still the geotechnical design, because ultimately which loads are going to be transferred to the foundation, the same which are obtained in the structural design. So basically the method of design should be compatible with structures as well as geotechnical. And therefore the people have made efforts in the Europe for LRFD method of design to be implemented for geotechnical as well as for the structures together. And Euro Code 7 is the exercise carried out into this. A exercise in great detail has been carried out, and it is implemented after 1995. It is in the practice, but you will see that there are so many anomalies still there in the LRFD method. IRC is also in the process of evolving the guideline, which is also based on EC7. Now this is applicable for bridges. It is not for building still. Okay, so for building still, our IS code is not doing anything for this. So for bridges, it is taking care for the cello foundation. So if somebody wants to take care of, use LRFD method for the cello foundation, whether cello foundation is for the bridges or buildings, it doesn't make any difference. Only thing is appropriate load combination should be used. So IRC 78/2020, first draft code, it was given in 2017. After 3 years, it is again updated as a draft code and put to the practice. So let us see when it comes. Now, for design of RCC beam, as I said, the partial safety factor for the material will be applied here in the FY, and in FCK. Okay. So with the application of partial safety factor here, the resistance calculation is directly a function of material properties. So we have to see the difference between a structural engineering problem, a RCC design or steel design, and geotechnical design. In RCC design, whatever the material properties we consider, it is FCK and FY, they are directly used in the resistance calculation. So moment of resistance is calculated based on these properties directly, FY and FCK. Whereas we see the cello foundation, design of cello foundation, ultimate bearing capacity, how it is calculated? ultimate bearing capacity is calculated as C and C, Q and Q, this equation which is adopted by IS 6403. Okay, so basic Terzaghi's equation, then Vincenzo equation, basic corrections and everything. So IS code has incorporated this equation. Now, what are the material properties for soil? The material properties we use for the soil are C and Phi. So the C and Phi are material properties, but you see that C is used into this, but Phi is indirectly used. How the Phi is used? Based on the Phi, we have indirect parameters NC, NQ, and N gamma. Okay. Now Phi is not having a direct into this equation. It is indirectly involved, and that also it will be in terms of 10 Phi and all. Okay. So once anything is divided by any partial safety factor is used for the Phi, it will not be directly used for these parameters. It will be having some different effect onto this equation. So Phi is an indirect parameter. Based on Phi, indirect parameters are used, and moreover, the resistance depend on type of value determined on this Phi. See, we all know that this bearing capacity equation is applicable only for general shear failure case, where the small strains are there before failure. Small strain occurs before failure. Okay. So when the material is not so good, it is not hard clay or it is not dense sand, in that case what will happen? Because the material is soft clay or loose sand, there will be large deformations occurring before failure, and this plasticity theory, this is based on the theory of plasticity, this equation is not valid. Okay, so for small value of Phi, this equation is not valid. So what we do? We carry out local shear failure equation. We work out local shear failure, and this is not based on the theory of plasticity. It is an empirical equation suggested by Terzaghi. Okay, so now this theory, the value of Phi with the partial safety factor when you are using, we know that for Phi less than 28 degree, it will be local shear failure. 528 to 36 degree, it's a mixed value. And 536 or more, it is a general shear failure. So equation is valid for Phi equal to 36 or more. Now suppose your Phi value is 36, you divide it by a partial safety factor here, then which equation will be valid? Which value of NC and Q we will have to use? Whether it is a general parameter or a local parameter. Okay, so there is a confusion into this. So the most important aspect of geotechnical engineering application is the soil properties are directly not used for the resistance calculation, but these indirect parameters are used for the resistance calculation. And that is the major limitation of implementation of LRFD into the geotechnical engineering. So let us see the quantitative approach also. So the ultimate net bearing resistance as per IS 6403 is, this is IS 6403 guidelines. Okay, this is the equation. Here you will be able to calculate NQ, NC, and N gamma based on the type of the footing. You can have the safe factor for various cases, that is for SC, SQ, and S gamma. It can be calculated like this. Depth factors are there, inclination factors are there. This is all from IS 6403. As I discussed, the theory is valid for only general shear failure. It is not valid for local shear failure. Now, what is the guideline given by the code? Code says relative density is equal to 70% or more. Void ratio is 0.55 or less. General shear failure will occur. If this criteria is satisfied, 30% relative density lesser than 30%, void ratio less than 75, more than 75%. I'm sorry, not less than 75. It is more than 0.75. Then local shear failure will occur. Otherwise, in between, a mixed shear. This is the guideline available in the code. Now, relative density and void ratio are not measurable parameters from the undisturbed sample. See, we have a cohesionless soil. See, for cohesionless soil, how to get the sample? We don't have a sample. Okay, undisturbed sample cannot be obtained. If undisturbed sample cannot be obtained, why to have guideline in terms of void ratio? You don't have void ratio. Okay, and we don't have relative density either, because for relative density you need a large sample to calculate gamma D maximum, gamma D minimum, and then you should have undisturbed sample for the calculation of relative density, gamma actual. So all these two parameters, they are not available in the actual practice. So how the actual practice goes? However, the relative density and the void ratio are the parameters used for the definition of the general and local shear failure. We are using phi value. If undisturbed samples are available, you can have laboratory test value directly. Phi greater than or equal to 36, phi less than or equal to 28 for local. This is for general. And here is for the mixed shear failure. So normally these two parameters are not used. Either n value is considered, or based on n value, we get the value of phi. So in most of the cases, our phi is based on SPT value. SPT test is also a very crude test. As I said, it is a very crude test. See, it is in the geotechnical engineering. It is said that you measure it with a micrometer. You measure it with a micrometer, then mark it with a chalk and cut it with an X. Okay, so what kind of accuracy is achieved into this process? Similar accuracy will be expected in the geotechnical engineering processes. So everywhere you will have to arrive at your own judgment, experience, and expertise. More or less, you have to have very good background about the empirical formulation. Okay, so all empirical formulation is going to be of great use in the case of geotechnical engineering. So my point is, this is general shear, local shear, and mixed shear failure have to be considered. So this cannot be done directly. Now, as I said, if your phi is equal to 36, so when you divide it by a partial safety factor, it will go either into the mixed shear case or local shear case, and your strength will be drastically reduced. So let us see the design of a shallow foundation for the mixed shear failure case of phi equal to 32 degree. So it is interpolated. The parameters are to be interpolated for phi equal to 32 degree to be a mixed shear case. So you find out the local shear parameter, you find out general shear parameter, and then you interpolate to get the mixed shear failure parameters. So all the geotechnical people who have done the bearing capacity calculations, they must be knowing. So we get mixed shear value of n cube 15.75. So this phi equal to 32 degree, if I am doing this footing, okay. So if general shear parameter are used, the strength is going to be bearing capacity, ultimate bearing capacity is 1107. Okay, 1107 kilonewton per meter square. 32 degree means mixed shear failure, then ultimate capacity is 770. And if local shear failure is considered, it comes to 327. So what is the variation of bearing capacity? We can visualize. For mixed shear failure, it is 287 to be considered. If you would have gone for general shear failure, Eurocode is silent about mixed shear failure and local shear failure. So the case in which mixed shear failure is applicable, Eurocode will go for what? It will go for general shear failure. Okay, and that will make the structure unsafe. So now let us implement limit state method for geotechnical engineering. This is what background was required for the working stress method. Now we transform to the limit state method for geotechnical engineering. So there are two limit state, ultimate state and service state. If we are having shallow foundations, then we have to take care for the ultimate state, and service state means settlement. Deep foundation also, we have ultimate state and we have a service state. For retaining wall, we do not go for service state. For slope stability, we go for ultimate state only. For excavation, we normally go for ultimate state, not necessary all the time. Because if there are adjoining structures, if there are supposed to be adjoining structures, you have to go for the service state also for excavations. Now, evolution of various design methods. So, in the geotechnical, it is mainly based on experiment and experience and learning from failure. So many retaining walls have failed, so many braced excavations have failed, and after that, Terzaghi has given that braced excavations cannot be designed with the active state of the earth pressure. Okay, so he has given the trapezoidal diagram for the distribution of earth pressure for the braced excavation. So similarly, for all the cases, we are having some presumptive values of the bearing capacity. There are empirical formulas available for, see, for settlement calculation, still we are relying on the N value versus settlement by Tang's equation or Tang's chart. Okay, so geotechnical engineering is more on the empirical side than on the mathematical side, because we don't have an undisturbed sample. So you have SPT N versus phi relationship, N versus relative density, N versus settlement relation, N versus SBC. All those empirical relations are in use. So that has to be considered while we are developing the LRFD method. And behavior for phi equal to 28 and phi equal to 36, it is not the variation of number to 8 degrees. Okay, it is not 1 degree linear. The difference is significant. When it is 35 to 36, it is a significant change. 28 to 29, it is a significant change. So all these methods require empirical way of working. Theoretical development is only for general shear failure. What about local shear failure for soft soil, weak soil? You don't have this the direct theoretical development. Okay, so all this we will have to rely much. We have to bank upon the empirical methods. So these are the geotechnical design approaches given by the Eurocode: designed by calculation, designed by presumptive measures, designed by actual load test, designed by the observational methods. So based on the different design approach, it will provide you different partial safety factors. So if designed by calculations are there, then your partial safety factors are only lower side. Then if it is based on the presumptive methods, your partial safety factor will be higher. If it is based on actual load test, then partial safety factor will be on the lower side. Similarly, it defines that what should be the factor of safety or margin of safety should be considered. It depends upon the type of the structure. So here 3 categories are defined: small and simple structures, okay, where negligible risks are there. Temporary structures like, so negligible risk is there. The conventional structure means no exceptional risk. That means your foundation soil is also good, foundation is also predictable behavior, and the structure is also having a predictable behavior. So all conventional structures come into the second category. And third category is special structures or difficult structures. So special structure means monumental structures. Suppose Sardar Patel statue. Okay, they cannot be designed for the same allowable settlement. Okay, so special structure can have different criteria. Similarly, if subsoil is not good, you are having an expansive soil, you are having a collapsible soil, or very loose soil. In that case, your criteria, your partial safety factor, your limits, LRFD criteria will be different. The Eurocode also defines ultimate limit state and serviceability limit states. So this is what the Eurocode is. Eurocode 1997 part 1. Now it is implemented against 2004. So these are the general rules for the, what is the content of the Eurocode 7. These are the limit states which are given. So Equilibrium limit state means loss of equilibrium. This is stability analysis. The second is equilibrium or stability analysis due to overturning and all that. UPL is because of the uplift. So if this is geotechnical, then there will be a uplift of the underground structure. So UPL state. Hydraulic heave, there is a seepage. So hydraulic heave also has to be considered. The structural part, that means the component of the structure fails. So this is a structural failure. So that is also considered to be a part of the Eurocode 7. And what we are interested in is the ultimate limit state for geotechnical case. So ultimate limit state for geotechnical case means foundations will be putting failure of the foundations. Okay. So this is when it fails. So we are interested in this case. So fundamental limit state requirements are this design or factored action effects. So action is considered by E. So E design is less than or equal to design resistance. Okay. Action effect, design action effect should be less than design resistance. Resistance has to be obviously more. That is the criteria to be satisfied. Now, how to find the design effect? So design effect is a function of what? Design is a function of loads and function of material strength. Okay. Design effect is a function of loads or action and material strength. So characteristic loads are multiplied by partial safety factor for loads, and characteristic strengths are divided by partial safety factor for materials. Okay. So load factor is multiplier and material partial safety factor is a in the denominator. It is a reduction factor. And third factor is how to find out design resistance. This design resistance is calculated using characteristic resistance. This is based on suppose a bearing capacity equation. Okay, RCH is resistance calculated from bearing capacity equation divided by partial safety factor for resistance. So how the characteristic values are to be determined for geotechnical engineering. So how to find out the value of C and value of phi? It is the most difficult problem. Okay, because you don't have much available data. If you are having a site, you do not get the statistical value. Most of the cases, what you have to do is you have to rely on the designer's expertise and understanding of the ground. Okay, see the last sentence is most important, that ultimately whatever is the data, you don't have many statistical values available because you don't have a homogeneous data encountered for any of the site. Most of the site, you don't have a homogeneous data. Even if it is a homogeneous strata, the value that can be obtained from the testing will be different because you don't get equally undisturbed sample. So the most important aspect of the LRFD application into the geotechnical engineering is defining the characteristic value of the geotechnical parameter. So how it is determined? So you have the field value or the laboratory value of the measured of a particular test, say n value SPT, or you are having n value to phi value, all this measured value. So suppose you are having a direct shear test and this subsample, C phi values are there. Then for empirical variation, you find out derived value. Okay, some other values you can get it from the actual load test. So all this, one will try to conclude the geotechnical parameter value. So after getting the measured value, you will have to use your existing knowledge and experience. See, so many times we have used our experience and knowledge that the value which is obtained in the laboratory cannot be correct. So we have to put those values aside and we have to use some other parameters or empirical values into the practice. Okay, so then it will become a characteristic value. So characteristic value means it will be moderately conservative. Okay, so if you are having the number of samples available for a site, what will be the criteria? 5% probability will be there. Okay, like concrete, I said, no, you are having 32 samples. And out of the 32 samples, if you get the variation of coefficient of variation of everything, whatever is the characteristic strength, it will be identified as the sample number of samples having strength lesser than the characteristic value for 5% of the samples. Now design of the shallow foundations for Eurocode. So it gives you this many combination. Okay, for action, only this particular, this with the block, these are the I mean the red mark, these are the applicable values unfavorable. Because in foundation we don't have any loading favorable. If it is a retaining wall, there will be favorable loading. Suppose overturning is considered, weight on the heel is a favorable load. In the foundation of everything we have an unfavorable condition. So dead load is considered to be the permanent load, imposed load is considered to be the variable load, and for A1, wherever A1 is there, it is 1.35 and 1.5, and wherever A2 is there, so 4 combinations are there. We will see that the DA1 combination 2 and DA3 are identical. So for soil, there are 3 combinations to be considered. So one is, what is the partial safety factor for action? 1.35 and 1.5. Okay. For dead load, it is 1.35 and 1.5. This is for A1 combination. For A2, both the values are 1 and 1.3. For bearing, the partial safety factor for the resistance. So what is the partial safety factor for resistance? R1, R2, R3 are there. So R1 and R3 are all 1. R2 is equal to 1.4. We are talking about bearing. Okay. So these are the partial safety factor for resistance. Partial safety factor for the soil parameters, if you see, then for M1 and M2, M1 means partial safety factor for material. So if you are using load combination 1, your partial safety factor for shearing resistance is 1. Okay. If you are using DA1, C2, then M2 combination. So what is M2? M2 you will have to take a value equal to 1.25. So that is how all the partial safety factors are used. So suppose you are having a value of phi, then it will be divided by 1.25. It is not phi is divided by 1.25. the 10 phi will be divided by 1.25. Okay, instead of 10 phi, factored value of 10 phi is equal to actual 10 phi divided by 1.25. So here, these are the 4 combinations to be considered. Okay. So this is what is required. 4 combination, permanent action 1.35, 1.5, material drained. So what we have is, we have a drained condition. We are using phi, suppose. So for phi, what is 1.35, 1.5? Dead load 1.35 times, imposed load 1.5. Drained means cohesionless soil. So partial safety factor is 1.1. Resistance partial safety factor is 1. Then DA1, C2, load factor is 1, 1.3. Drained is 1.25, and resistance is 1. And then DA2, 1.35, 1.5. Material is 1, and resistance is 1.4. So after doing all this, what you have to do is design resistance has to be less than design load, design action should be less than design resistance. A sample problem conforming to Eurocode 7 is done here. Okay. So these are the data. This is the data. Length, width is equal to 2 meter. Depth is equal to 2 meter. Dead load is 2000 and live load is 1000. So total load is how much? 3000 kilonewton load is there. Phi equal to 36 degree, gamma equal to 18. Okay, reinforced concrete is 25 kilonewton. So partial safety factor A1 and A2 1.35 and 1.5 for dead load. Okay, for dead load it is 1.35 and 1.5. Dead load 1.35. So this is DA1 C1. So vertical load becomes how much? Factored vertical load, it becomes 4200 kilonewton. Actually it is 3000. Okay, 2000 and 1000. When it is factored, 1.35 dead load, 1.5 imposed load, it becomes 4200. Now area of base how much? 4 meters square. So how much is the design bearing pressure? 1050 kPa. So now DA1 C1 calculation. Okay, for phi equal to 36 degree, what is the partial safety factor you have to apply? And partial safety factor is 1. So your factored value is also 36. And what you get is NQ, N gamma. And you put it in the bearing capacity equation. Partial safety factor for R1 is also 1. So what you get is for DA1 C1, you are getting the ultimate resistance equal to 2833.65. And this is the design resistance 2833 multiplied by area. Okay. So area is equal to 2 by 2. So you have action, design action is 4200, design resistance is 11,000 according to DA1 C1. You consider DA1 C2 and DA3 both are identical. So when we do it, the exercise 36 degree angle, it becomes how much? Because it is divided by 1.25. The material safety factor is 1.25. Okay, so 36 divided by 1.25 becomes 30.16. So your parameters becomes NQ and gamma 20.62. So bearing resistance is how much? 1271.77. So resistance factor, total resistance is how much? 5,000 kilonewton, and total action, design action is 4,200. So then design approach 2, DA2. Here also you are getting 8,097 and 4,200. So that means governing criteria is this much. So a 2 meter by 2 meter, you are having the minimum RD divided by VD value, that will be considered to be the design value. Okay, where this ratio is minimum, and this ratio should always be greater than 1. So this is satisfied. Now, to identify the limitation of this method, I am carrying out a parametric study. Okay, I'll take 5 more minutes. A square footing is put at a depth of 2 meter. Gamma is equal to 18 kilonewton per meter cube. I'm using a dead load of 80 and live load of 40 tons. 3 different problems are considered for angle of internal friction: 28, 30, and 36 degrees. The width of square footing will be obtained based on the IS code. So to resist the load of 80 ton and 40 ton, what is the width of footing required for all these cases, 28, 30, and 36? What I will be doing is, I have calculated this width required as per IS code. So if you will find resistance upon the action for IS code, how much it will be? It will be very close to 1. So for IS code method, I am using for proportioning. Okay. So first footings are proportioned according to the IS code. And then for whatever width is calculated as per IS code, I am calculating the resistance of the footing as per Euro code. Now I am considering 2 cases. While calculating the Euro code resistance, without considering the type of failure. Here, resistance calculated for 2 considerations. One is without considering for type of shear failure, and to take into account type of shear failure. Suppose it is 36 degree, okay. So when it will be divided by 1.25, it will be a reduced value. So for 36 degree, the reduced value is suppose say 30 degree. Then for the 30 degree, what should be the value of the shear failure? For 30 degree, I will not be considering type of failure. It will be considered as general shear failure. That is case 1. And case 2 means 36 degree in the IS code is a general shear failure. But if it is a reduced value in the Euro code, it should go to a mixed shear or local shear. So type of shear failure also has to be considered. These are all the load combinations to be taken into account. 1.35, 1.5, 1, 1.3, and this table is prepared. So have a look at the table. I'm designing the footing as per the IS code. ASD is the first column. It is IS code. Okay. So their ratio is 1.02. That means the width of the footing 2.9 meter is designed based on the IS code. Okay. So it will be 28 degree. It will be a local shear failure. When 28 degree is treated as general shear failure, the resistance becomes very large because 28 degrees is treated as a general shear failure. And when 28 degree, whatever is the type of failure, it has been accommodated, it is a local shear failure. So factor, it becomes R upon Q, it becomes a factor. Okay, so resistance is much higher. Okay, so resistance calculated is much higher than the IS code. So here the governing criteria is, if it is considered only general shear failure, then for general shear calculations, the governing criteria is 3.53. Smallest of the three, 5.26, 3.53, and 3.75. Smallest is 3.53. So resistance calculated by Euro code is 3.5 times higher than the IS code. Okay, resistance calculated is 3.5 times higher than the IS code. That means it is on the unsafe side. If I am using general shear failure, resistance calculated is 3.5 times higher than the IS code. That means it is unsafe side. If I am considering the local shear failure, this margin, the higher calculation is on the of the order of 30%. Okay, so this is for phi equal to 28. Now come to this 30-degree value. So what is the, if it is calculated on the general shear failure, so if it is directly calculated on the general shear failure, the maximum value is 2.475. So it will be 2.47 times higher resistance. Okay, it will be offering 2.47 times higher resistance if it is treated as general shear. Basically, the value of phi becomes high, how much? 25. Then value of NC, NQ, and gamma should be based on local shear failure. Okay, because phi value is 25, it should be calculated based on the local shear failure. So local shear failure should be considered, and it gives you a smaller value, 0.95. So this resistance calculation, because it is taken on this side, 2.47 is the higher resistance calculated. So if you design it with the Euro code and without considering the type of the failure, your foundation is going to fail. For phi equal to 30 degree, your foundation is going to fail if it is designed based on the general shear failure. And on the local shear failure, it will be very close to this. And for 36 degree, if you see, here IS code is 1. What is the governing criteria? Because it is general shear failure, here the value is 1.02. It is almost near. So when phi is equal to 36 degree, your general shear failure criteria, it works well. But if you have considered the reduction, in the phi value, 36 divided by 1.25, in that case, it goes to the mixed shear failure case and it becomes 0.5. So what has happened with the general, 36 degree, that with the general shear, it complies. But with the case of mixed shear, the foundation size will definitely increase much higher. Okay, so this is the anomaly what I wanted to highlight. So for all phi value less than or equal to 28 degree, all the Euro code assessed value with the general shear failure only, it will be on the much higher side, resistance is on the much higher side, and that is unsafe side, 28 degree and less. This will be unsafe side. Whereas here phi equal to 36 degree and higher, it will be okay. Okay, but to overcome this 28 degree higher evaluation, what I should do is I should go for the local shear criteria calculation then it becomes fairly 25% here and there is fine. So if I am implementing the mode of shear failure to be accounted for on the factored phi value, if mode of shear is accounted for in the factored phi value, then 36 and higher values are becoming much lesser. So this is the major anomaly in the Euro code 7. So you can visualize with this. Okay, so 28 degree and less, accounting for the type of shear failure, which will be on the higher side, and 36 degree and more, here accounting for the type of shear failure, it will be on the lower side. So that is the anomaly, and that has to be overcome. We are working on to that instead of applying the partial safety factor to the phi value, we should apply the partial safety factor to the parameters which are based on the pi value. So instead of applying partial safety factor to phi, we should apply partial safety factor to NC, NQ, and N gamma. That will relieve all the problems. Okay. So from the given phi value, you first find out NC, NQ, and N gamma based on the type of value, and whatever partial safety factor is to be applied, it should be applied for NC, NQ, and N gamma instead of applying it to the phi values.
Hello, am I audible, sir? Hello, hello. Uh, Hello. Please wait a while. I think there is a network issue from expert side, so we'll join soon. Please wait. Yes, sir. You are back here again. I guess the network issues will be there. Hello, am I audible, Shed, sir? Hello. Hello. Hello, am I audible, Shed, sir? Hello. Dear participants, please sorry for inconvenience, but please stay with us. Expert will join soon. I think network issue is there. Hello, sir. Can you listen us?
Yes, yes.
Okay.
Okay. So when I rejoined, no, that was muted.
Okay. Sir. That is fine.
Okay, so that's all from my side.
Thank you, sir. If any participant wish to interact with the expert, if any question. There are any participants who wish to interact with the expert? Okay, sir, I have a very small question. Sir, it is in regard of bearing capacity calculation with the IS 6403. So, sir, we know that the depth factor calculation depends on the value of the phi.
Yes.
Okay. Root n phi is there. So, in case of local shear failure and mixed shear failure, should we consider original laboratory phi value, or we should consider a reduced value of phi? Because day factor is taking care of the soil which is being compacted in the compacted surcharge soil. So shall we reduce the value of phi, or we should use original value of phi?
See, bearing capacity calculations in 6403 are for the natural values of the phi, no?
But in case of local shear failure, in case of local shear failure, shall we use reduced value phi prime, or we should use the original value of phi?
No, that should be the reduced value, no?
Okay. But
For
isn't it,
local.
sir? Because in either some part of the surcharge soil is taking care in the shear failure. Okay, so isn't it like we are reducing the phi value for the soil which is being taking part in the shear failure? So isn't it
No,
for
see,
that soil only we should
basically,
reduce the value?
the backfill is not considered to be taking part in shear failure.
Yes, exactly.
So whatever soil is existing beneath the footing, no, that is only considered for the bearing capacity calculation.
Okay,
the soil above the level of footing is treated as surcharge.
That's yes, exactly.
So
that's
its
why I'm
weight is
asking
only
that.
that's only weight is considered.
Okay, that's why I'm asking that for that soil, because day factor is taking care for that surcharge soil. So shall we use that original phi value or reduced phi?
For surcharge and all that so surcharge is not treated as a phi resistance. Okay, so surcharge is considered to be a weight only. So surcharge soil you do not consider phi value. Okay.
So in short, in calculation of root and phi, and 45 plus 5 by 2 is there.
Yeah. So
so in case of the local shear failure, we shall use the reduced value of phi. Is it?
See, in the depth factor, you can use the just I'm getting this.
Because we know that the surcharge soil is not taking part in the shear failure. So that's why I'm confused that shall we use the original value of phi for depth factor calculation or reduced value?
See here depth factor for sea soil only it is there. The value of phi less than 10 degree it is 1, and dq for phi greater than 10 degree it is 1 plus dq by root 10 phi.
Yes,
okay.
That's what I'm asking.
10 45 plus 5 by 2. Here this phi value should be phi of the backfill.
Okay, means yes, sir. In the homogeneous backfill, if the homogeneous soil is there,
of the backfill.
then yes, shall we use the original phi value?
That is original phi value. So here it is original phi value. Local shear for only the bearing capacity factor. It is not for this factor.
Okay. Means
so
in all the case we shall use the original phi value.
So here original of backfill.
Okay.
This is the original value of backfill. This is a good question.
Yes. I was a bit confused about that. So, what should we use, because we know that the surcharge soil is
when
not
it
taking
comes
part
to audit,
in the,
no, when it comes to audit, this becomes a problem. So here it is backfill.
Even though the difference with the original value and reduced value is not that much, still it is a point of concern that what shall we use?
Yes.
Okay. Thank you, sir. Thank you.
Okay,
And
thank you.
Sir, some more question is there in the chat box. Please wait. So, sir, one question is why Eurocode is suggesting a very low factor of safety as compared to Indian standard?
They rely very much on their testing standards.
Okay.
Their testing standards are much better than our standards.
Okay.
So, their factor of safety, they are relying about 2.25. Our factor of safety minimum is 2.5.
Okay, okay. And sir, one more question is, what is your opinion about pending revision of IS 456?
The coming revision of IS 456 is already in the progress. Okay, Professor CVR Murthy is taking care for that revision. So basically it has to come by now. Enough time has gone into, but right now nothing is there. So we are still waiting for revision of IS 456.
Okay,
And it is basically to take care for the high grade of concrete.
okay, okay, sir. Okay, thank you so much. Thank you so
Okay.
much.
Any questions from participant side? Okay, sir, I think there are no more questions with us. So I thank you, sir, for sharing your valuable time and the experience with us, for guiding us towards the importance of the partial factor safety approach in reference to the working stress method and the limit state method. In both the field, that is the structural engineering as well as in the geotechnical engineering, where especially whenever we are designing the foundation, so which particular factors we have to always keep in mind with reference to the IS 6403. So it was a very great session for us, sir, and hope the participants has also find this session very interesting, and that will also help them in doing their further studies. Thank you, sir, for the great session.
Thank you. Thank you all for having a patience learning.